Are you wondering how you can design and build independent systems that can evolve, scale, and operate individually, yet still communicate effectively to form part of a larger application? Well, thank you for joining me today as I share some application integration patterns for microservices. My name's Julian Wood, and I'm a Senior Developer Advocate here at AWS Serverless. I work with builders and developers to help them understand how best to build serverless applications, as well as being their voices internally to make sure we're building the best serverless products and features. Prior to this, I was an infrastructure engineer, architect and manager for many years, and I've worked in large global enterprises as well as startups. I've been using and talking about serverless for a number of years, helping the world fall in love with serverless, just as I have, and now I get to do this at AWS. Please feel free to contact me at any time with your serverless questions, whether you have questions from today or other general questions around development. And you can reach me via email or Twitter anytime. When it comes to software architecture, there are two really helpful principles to allow you to build effective applications. The first is divide and conquer. This means breaking up your application into smaller microservice components. That's the dividing them part. This gives you the benefit of having each part work independently. It runs in a way that's best suited for that component, and that's the conquer part. Once you do that, you then need these different parts of your application to work together. This is the coupling part. But you don't want your microservices too dependent on each other, or you're back to having a large, unwieldy application. So you do want coupling, but loose rather than lousy coupling. And the best way to achieve that is with asynchronous messaging. Many customers think for microservices to communicate, you need to have a REST API and have services call each other via this API. However, you don't always need to manage an API between your services, and asynchronous messaging can give you a number of distinct architectural advantages. So this talk is all about integration patterns that are based on messaging, with the goal being to have independent systems that you can evolve, scale, and operate individually. Now, you may be thinking, hang on, why are application integration patterns only applicable for microservices? Shouldn't these patterns be helpful for many kinds of architectures? And you're absolutely right. That's why this talk could be also called Application Integration Patterns, not only for microservices, because the patterns are useful in many situations, even communicating between separate applications or even organizations. But the architectural advantages of using asynchronous messaging really shines with microservices. I'm going to start with introducing why asynchronous messaging is useful, the benefits, and some of the drawbacks with synchronous messaging. I'm then going to show some integration patterns based on messaging and how to use them individually and also together to give you messaging superpowers. And then bring all these patterns to life with some relevant use cases so you can see how they would work in the real world and hopefully understand how the benefits could apply to your own applications. So let's talk about why we need messaging in general. I really love this quote from former colleague at AWS, Tim Bray, who said, "If your application is cloud native or large scale or distributed and doesn't include a messaging component, that's probably a bug." If you're building real-world production applications, you really need to be thinking about messaging. Looking at synchronous systems, well, what are some of the drawbacks? Synchronous systems come with an implication. They are tightly coupled with tight dependencies. A request that comes in from somewhere to your microservices application can take a complex path with many hops. If something goes wrong with any one of your downstream components, this has an immediate impact on your upstream callers. For example, you still want to be able to accept orders from your customers, even if your downstream email notification system is having an issue. This is difficult with synchronous systems. An error or increased latency in some part of the application can affect other unrelated parts and can result in a poor experience for your customers. And some things just take time to process or are already asynchronous, such as sending that confirmation email. But now let's carry on and start to look at some application integration patterns using messaging. Patterns are a helpful construct for architects and builders because they provide a common language so everyone can understand what is being talked about. And starting with a fundamental pattern, message exchange. There are two basic ways to exchange messages between systems, one-way and request response. For one-way messaging, there's a sender and there's a receiver, and there's a message channel, which is some kind of logical communication link between the two. This message channel decouples the sender and the receiver so they don't have to directly know about each other. The sender sends messages into the channel, and the receiver then receives the messages out of the channel. The sender does not expect a response from the receiver directly, it only expects a response from the message channel to confirm the message has been sent. For the other pattern, we have request-response. Here the request and response are separated into different channels. The requester sends a message to the first message channel, shown here on the top, and the responder responds back via the second message channel, shown here on the bottom. Now, you may be thinking, how does the responder know where to send the response back? It doesn't know about the requester, only about the channel it's receiving messages from. Also, how does the original requester know how to correlate a returning response to a previous request? And this works by using two patterns, the return address pattern and the correlation ID pattern. The requester injects a little bit of metadata to the request message, which the responder extracts and can derive the address of the return channel. The requester also adds a unique correlation ID to the request message, which the responder passes back into the response message so the requester can correlate responses to original requests. Let's look a little more deeply at what these message channels actually are. We can look initially at two types of channels, point-to-point and publish-subscribe. Point-to-point is implemented by using queues. We have a sender, shown on the left, that sends messages into the queue. There can be multiple senders sending messages onto the single queue. I'm just showing one here for simplicity. The queue then has a receiver, which is shown on the right. Every message sent to the queue is only received by one receiver at a time. There may be multiple receivers to scale out the processing of the messages, as shown here. The queue distributes the messages across them, but each message is only processed by a single receiver at a time. You can see here messages A, B, and C are sent to the queue, and each then delivered and processed by one of the receivers. This provides two powerful advantages. First of all, you can scale out your receivers. If there are a lot of messages added to the queue and existing receivers aren't able to handle the load, you can add more receivers and the queue distributes the additional messages to the new receivers. In this way, the queue acts as a load balancer. If the queue stores messages before receivers process them, it can also act as a buffer, which is helpful to flatten peak loads. The messages don't have to be consumed straight away. They can stay in the queue and persist until the receivers can process them. This helps to control how fast messages are processed, which can be useful to manage how many receivers you need and also protect the load on downstream resources. This has another helpful side effect, that you can safely take your receiver's processes offline for maintenance work. There's no danger you will lose the messages as they are buffered and persisted in the queue. When the receivers come back online, they can continue to process the messages in the queue. Let's take a look now at how publish-subscribe works, which uses topics. Again, we have one process on the left-hand side that submits messages into the topic. It's called the publisher. Again, there can be more than one. On the right are what are called subscribers. The topic behavior is a little different because every message is normally delivered to every subscriber. Think of it as a broadcast. You can see here messages A, B, and C are added to the topic and each subscriber gets A, B, and C. For queries, we saw that if the load becomes too much, you can scale out the receivers to process the additional load. That doesn't work for topics, as each subscriber receives every message. So you can't scale out the subscribers in the same way. Each new subscriber receives all the messages. Also, with topics, messages are usually not persisted. That means if one of your subscribers is offline, they will lose all the messages as long as they are offline. But don't fear, we can combine queues and topics to help with this. AWS has a number of services to implement the messaging channels I've been talking about. Let's begin with the cloud-native ones. We have Amazon Simple Queue Service, SQS, for the implementation of queues, and we have Amazon Simple Notification Service, SNS, for the implementation of topics. As I said, these are both cloud-native and both are serverless. This means that there's no infrastructure to manage for you whatsoever. You simply consume the functionalities through a simple API and pay purely based on consumption. Both services can act as event sources for AWS Lambda. This is our serverless compute service to do the processing on the messages. If you have a requirement to use industry standard messaging protocols like JMS or AMQP, maybe you have a legacy requirement or a lift and shift scenario, we have Amazon MQ. Amazon MQ is a managed service that can manage well-known message breakers on your behalf, and these include Apache ActiveMQ or RabbitMQ. If you use Amazon MQ with Apache ActiveMQ, it can also act as an event source for AWS Lambda. Another publish-subscribe option is an event bus. An event bus has one or multiple publishers and one or multiple targets. The event bus acts as an event router. You set up filter rules to route incoming messages, which are called events, from the publishers to specific targets. An event bus is useful when you have a number of different types of messages that you want to route. AWS has an event bus called Amazon Event Bridge. It's serverless and cloud native. Again, no infrastructure to manage. You just pay per use. EventBridge allows you to publish events directly from multiple AWS services, your own custom application events, and integrated SaaS partners directly into event buses in your account. You then create filter rules based on the content to route the event messages to various targets. And these can be AWS services, including AWS Lambda and step functions, as well as any API destination. Back to the patterns. You can create compound patterns by combining some of the fundamental ones. Topic queue chaining is a useful pattern to solve our previous problem of how to scale out the subscribers. We have a publisher, as before, that publishes messages onto a topic. But we don't directly attach our consumer processes to the topic, but we rather put a queue in between. And then our consumer process pulls the messages off the queue, and with that, we get the best of both worlds. We can have fan-out functionality, and at the same time, we also have consumer scale-out. Also, because the message queues can buffer and store messages for us, we add extra resiliency. If there's an outage on one of the receivers, the messages will not be lost. And we can also safely take our consumer processes offline for some maintenance work. Sometimes you have requirements where preserving the message order is really important. Maybe processing a payment before an order is confirmed. SQS standard queues don't guarantee the ordering of messages. It's best effort ordering. But for this case, we have a type of SQS queue called a FIFO queue. That's first in, first out. And as you can see in the example, the message order is preserved. However, preserving order is a very difficult thing to do, particularly in a multi-threaded environment. And so FIFO queues don't have the same message throughput as standard queues, and this is common across most message queue systems. For SQS, standard queues can support nearly unlimited transactions per second. When considering FIFO queues, there's something else you need to think about. You also need to think about receivers. You can't scale out receivers in the same way. You can't have more than one receiver if you need strict message ordering. If you do have multiple receivers acting concurrently on the incoming messages, you obviously can't guarantee the message ordering on the receiver end because the processing time for each message won't necessarily be the same. So what can we do with FIFO queues to still have at least some scalability on the receiver side? We can use the message group pattern to allow you to group multiple messages into a group by adding a property to the message. The messages within the same group are then always processed in order. Messages that belong to different message groups might be processed out of order. Looking at the example, we have three message groups. Messages A and C are in the same message group, color-coded orange. B is in its own purpley message group, and D is in its own blue message group. Message A is delivered to one receiver. Message B is then delivered to another. Message B is consumed. In the order of the messages in the queue, message C should be delivered, but not with message groups. SQS parks the message while the same message group within the same message group while the previous message is in flight. In this case, message A hasn't been consumed yet. So instead, the next message D, is delivered, and message D is then processed. When message A is eventually processed, it's now done, and now it's only a matter of concurrency. any of the available receivers can process message C, and in this case, the receiver at the bottom receives message C and processes it. And this is how you can scale your receivers out with FIFO queues using message groups. Carrying on with some other helpful message routing patterns, the message filter and the recipient list pattern. For topics, I've explained how every subscriber receives every message from the topic, but there may be times where some of the subscribers are only interested in a certain subset of the messages. In this example, the subscriber at the top is only interested in orange messages. The one at the bottom is only interested in purple messages. As these are decoupled, the publisher is unaware of what each subscriber needs. Now, you could add a dedicated topic for each of these cases, but if you have a lot of permutations, this can quickly become tough to manage. So what helps here is the message filter pattern. Each subscriber individually agrees with the messaging system that it's only interested in a certain subset of the messages. In this case, either orange or purple. And this is usually done by filtering on meta information that is part of each of those messages. And staying decoupled, the publisher on the left-hand side doesn't need to be aware of this. It's interesting to compare this to the recipient list pattern, which does the same thing but doesn't use decoupled messaging, and so is harder to manage. Again, we have a publisher and subscribers, and there is something now in between them, some sort of system or process, some code that implements the recipient list functionality. This knows which subscriber is interested in which messages. However, this means it's code that you need to manage and maintain with some additional infrastructure, and also means the publisher and subscribers are more coupled, an example of lousy coupling. Message filtering is therefore a better option to choose in this case and highlights the advantages of decoupled messaging. And there's another message routing pattern that's very helpful, particularly with parallel processing, and it's called the scatter-gather pattern. And it's a really great pattern for use cases where you need to distribute requests across potentially interested or relevant parties, and you need to capture their individual responses, maybe to decide on the best response, or you need to aggregate responses, or maybe both. And again, it's a simple composite pattern. Think of a request for quotes or RFQ process. You can use topics in the beginning. A requester sends out an RFQ to potential responders, your vendors maybe in this case, who then receive a copy of the RFQ. The responders then work on their individual quotes and send their responses back to a queue using the return address pattern, so they know the address of the response queue. From there, the individual responses are consumed by an aggregator component. This could be to choose the best response or aggregate the results for some analysis. Finally, it's processed by a processor component, and using the correlation ID pattern, all the individual responses and the aggregate response are correlated to the initial request. If you are wanting to implement a sequential processing pipeline, you can implement the pipes and filters pattern. You have an event source and a result target. You can have maybe multiple steps in between where some sort of transformation or calculation is done on your initial event. You use a message queue and a piece of code for each step. This could become quite a long pipeline. Each filter step needs to know about the next step, and you'll end up adding quite a bit of coupling in your pipeline. So it may not be the best way to implement something like this. A better solution might be a pattern like Saga orchestration. A Saga is a sequence of local transactions. Each service in a Saga performs its own transaction and publishes an event. The other services listen for that event and performs the next logical transaction without tight coupling, and everything is event-driven. Again, we have an event source and a result target, and we need to perform multiple transformations in between. We then introduce an orchestrator component into the pattern, which moves the knowledge of the processing steps into the external orchestrator rather than with each individual pipeline step. The orchestrator handles the coordination between the processing steps, creating a workflow. Participants remain as loosely coupled as possible. The orchestrator allows you to implement traditional workflow capabilities such as transactions, or could be branching, retries, and parallel processing. To use this pattern, it's worth looking at AWS step functions as your orchestrator. Step Functions is a serverless and cloud-native service which implements state machines so you can apply the Saga pattern. You can define these state machines in a JSON or YAML document, or even create them graphically in the AWS Management Console. I've been through the important patterns now. We have enough to apply them to real-world use cases. Wild Rides is our favorite fictional technology startup, disrupting individual transportation by replacing old-fashioned taxicabs with unicorns. It's much more fun and obviously way more magical to ride with unicorns, of course. They are a modern technology company using serverless microservices and asynchronous messaging to iterate and scale faster. The first use case is submitting a ride completion. Imagine a unicorn has just dropped you off back home after a trip. The unicorn wants to inform Wild Rides that the journey is finished and also make sure that Wild Rides collects the fare from the passenger on behalf of the unicorn. The unicorn uses the Wild Rides Unicorn app. There's a button that they can press to send the right details to the backend of Wild Rides. The app uses a REST API resource for this, which includes the ride details as part of the payload. This API resource is implemented by the Unicorn Management Service in the backend of Wild Rides, and I'm leaving out some architectural details to simplify the explanation. For example, there's an API gateway in front of the Unicorn Management resource to make sure that we separate the actual API from an implementation. The Unicorn Management Service starts by persisting the ride details in the rides database. This creates a new ride resource and responds to the app saying the request has been received. So the client can now continue with other things while the backend deals with the request asynchronously. As I said, Wild Rides have a whole set of microservices, and some of them may be interested in a ride completion event. Here are a few examples, such as the customer notification service, accounting service, a loyalty service, and a data lake injection service for further ride analysis. There's also a special service, the Extraordinary Ride service, which is only interested in rides with a fare and distance above certain threshold values. So how do we integrate all of these services? The first option you may think of is integrating everything via a database. The Unicorn Management Service already has a database which stores all the ride details. We could simply share the database with all of the services on the right-hand side. We could do this, but this means we would be tightly coupling all the services on the right-hand side to the specific database schema. Any changes could break every other service integration that we have here. And this is another case of tight coupling that would be lousy coupling, which we don't want. So, of course, we don't want to do this. We could integrate all the services via REST APIs. REST APIs are often a great choice with many use cases, and I'm a big fan of REST APIs. And it's an absolutely valid approach here, but it does come at a cost in this scenario. With a REST API on each individual service, the Unicorn Management Service needs to know about all the endpoints, and to add any more microservices, you need to update the Unicorn Management Service. Or maybe externalize it into a separate request distribution service, but that means more code, more infrastructure for you to manage. We also still have to cater for the Extraordinary Ride service, which only cares about the relevant messages. Again, more if-else code in the distribution service, something which we could potentially avoid. So there's another option. The best way to integrate this scenario is using messaging. I'm sure that's not going to be a big surprise to you as you've been seeing all the benefits I've been going through. So we could add a ride completion topic here using the publish-subscribe pattern. May as well use an SNS topic. It's serverless, there's no infrastructure for us to manage. And all the interested microservices on the right-hand side can simply subscribe to it and receive every message that the Unicorn Management Service puts into the topic. And using SNS's message filter functionality, the Extraordinary Ride service can simply set up a filter policy to only receive the relevant messages, and there's no additional code for us to manage for this either. And if you want to add more resiliency here, we can also add a queue in front of every service using the topic queue chaining pattern. This allows us to safely take down the service for maintenance. We won't lose any messages and also gives us a lot more scalability. The second use case is called Instant Rides RFQ, Request for Quotation. Wild Rides has a great idea. They don't just want to match the closest available unicorn for a ride. They'd like to ask all available nearby unicorns to submit their individual offers, and customers can select the best one for them. And yet, this may be the cheapest one, but it could also be the one that has a great sound system or free drinks available on the ride. Their cleverless serverless architects decide to go with a scatter-gather pattern, which seems like the best fit for this use case. The Wild Rides customer uses the Wild Rides customer app. They enter the ride details in the app, where they want to be picked up and where they want to go, and this is submitted as a request to the back end, likely via an API gateway resource fronting the ride booking service. An RFQ response isn't going to be immediate. It's going to take some time to get all of the responses back from the local unicorns. Wild Rides gives unicorns 2 minutes to submit their individual offers. The customer doesn't have to wait and keep the request open all that time. The ride booking service creates a task resource, which is sent to the client with a link to refresh the task resource representation. The client can continue processing other things while the ride booking service processes the request asynchronously. In the backend, the ride booking service publishes this RFQ onto an SNS topic. On the other side of the topic, we have a unicorn management service, which has resources for every active unicorn. So only contact the unicorns that are in the area where the ride should start. Maybe we have a topic attached to a certain geographic area. The unicorn management resources in that area are then subscribed to that topic. The unicorns are notified there's an RFQ through the Unicorn app via a push notification on their mobile device. The unicorns can then work on their individual offers and send them back through the app to the unicorn management resource, using the return address pattern, sending their response back to the correct response queue. The ride booking service consumes those responses from the queue using the correlation ID pattern to assign the incoming responses to the original request. While this is running, the customer may want to get an update on the status of their RFQ using the Retrieve RFQ Status resource link to check if the RFQ is still running. Once the RFQ is done, the status reports it's done, and then it comes with a link to retrieve the actual final result. And the client retrieves the results, probably in an array of quotes, and the app can visualize the quotes that came in from the unicorns with the additional options, and the customer can make their choice. So, to wrap up, let me summarize what I've been through during this talk. I highlighted the benefits of asynchronous messaging compared to synchronous messaging for your microservices communications. I went through some fundamental integration patterns that are based on messaging and how to even combine multiple integration patterns. And then, to bring it to life, I showed how to apply these patterns in real-world scenarios with microservices using our fantastic startup, Wild Rides. To learn even more about asynchronous messaging, here are some resources which are also linked to via the short link and QR code. There are a number of AWS blogs on our public compute blog website tagged with messaging, so they're easy to find. There's also a super useful hands-on workshop that implements the patterns and the use cases that I've presented during this talk, and even adds some more. And this is really a great way to play with asynchronous messaging yourself and see how the code and the integrations work. And we also have application integration immersion days, which can help with implementing your workload in the cloud. So please contact your AWS account team to set this up. And lastly, if there's one thing to take away from this talk, and not forget, loose coupling is always better than lousy coupling. Also, for plenty more serverless information, head over to serverlessland.com with lots of resources, blogs, videos, workshops, and learning paths. Everything about serverless on AWS. And you joined AWS Summit to learn, and you can keep learning beyond the summit with resources from AWS training and certification for serverless and containers. We offer online digital training that is available on demand. You can also explore labs, white papers, and other technical resources by downloading the AWS Ramp-Up Guides. For more information, visit aws.training/learning library and select the serverless or containers domains. Thank you. I really appreciate you taking the time to watch today, and hopefully I was able to help you understand how asynchronous messaging can help your applications communicate, and you can put what you learned into action. Please do not hesitate to contact me if you have any questions. And at AWS, we always really value your thoughts so we can continually improve based on your direct feedback. So please take a minute and fill out the session survey.